The final transformation type is scaling. We can change the size of objects as well using the same matrix. And there is also an illustration for that from the Red Book. Scaling this one. It's interesting because they tried to describe everything in the same drawing. Because scaling can also be used to reflect stuff around the axis, so you can sort of invert it. If you use a negative scaling value on one of the axes, then the object is sort of turned inside out. Yeah, and as well, this also stretched on the x-axis, so it's to illustrate that you can do all of this with the same scaling operations. You take the original flower pot and you can stretch it on one axis, and then you can reflect it on the other axis. So that will be a value of maybe 2 or 3 on the x, and the value of -1 on the y, and a 1 on the z. It stays the same on the z axis. That is called a non-uniform scale. It can be useful to create objects that look different. Like in Unity, when we want to make a rectangle, we create a cube and then we scale it by a non-uniform value. Uniform scale, of course, just changes the size of an object. And with negative values is possible, but you don't use it so much. Flowpot. Yeah, I wonder what that is. So I think it's probably a value of 3 around the x-axis. But also there's this -1. I say along each axis. It's not around the axis. That would be a rotation that takes place around the axis. With scaling it's the same. So the rotation around the z-axis actually affects the x and y coordinates. That's why we say around the axis. On scaling it's along the axis, so it's the same coordinates that's affected. So along the x-axis actually changes the x-coordinate of the vertices. So we can define the scaling factor also as a vector, which is usually done. We can call it S, and it's just these 3 values put in a vector, a scaling vector. We say Sx, Sy, Sz. Running out of room. See if you can fit. So scaling matrix. Should move stuff. Out here. There. So the values go to the diagonal of the linear 3x3 matrix. And it's a linear transform for this reason, i.e. the translation part is all zeros. Okay, just going to bring up the pipeline again so we can see where we are. This one. We most have been talking about this step, although this step has exactly the same operations. So the modeling transform and the viewing transform. But now we are looking at this step specifically, how to define where the camera is in terms of transforms. Call this a virtual camera. And I have a drawing of a camera. It's not this one. Yeah, actually it is. This is a drawing from the Red Book. So I think I use... bigger. We want to place this camera in space, and we have this viewing volume, which is just defines what we can see, what the camera can see. So it's like a subset of the space where the camera is, and anything that's inside this can be seen on the rendering, and everything outside is not seen. First of all, the camera is positioned, of course. We place the camera somewhere in space. So let's say we have like a world coordinate system. The world is here. Everything at this point at the place of the view transformation is defined in world space. Everything is in world space at this point. Thanks. World coordinate system. So the first thing we do, or one of the things we do, is to translate the camera to place it somewhere in space. So we can imagine that there's a vector that goes up here. Now I say the center of the camera is there. 1 minute. Go away. Thank you. From the origin to this place. This is a translation. So we can define a vector that sets the position of the camera. Let's use the purple color like here. And then of course we want to orient the camera as well, so direction it should point. And that's slightly more involved. So here I'm going to draw 3 vectors, which is kind of the camera's local coordinate system. The convention is to use red for X, green for Y, and blue for Z. So we draw an X-axis like this, and then we draw a Y-axis here, local camera coordinates, and then a Z-axis that points in the direction of the view. The latter we call the view direction vector. You can also call it Z. Z vector of the camera sometimes. So that's a vector. We also have to define, the camera needs to know where it should look, but it also needs to know how it should be turned, so what is up. So we use an up vector for that, and that's the y-axis. View up vector, or y. And the last one is a I mean, it's less important because it can be worked out by the graphics hardware. If we just tell it we want to look in a certain direction, give it a vector, and when we say this should be up, then the third one, the system could simply take a cross product of those two and work out the third vector so it has a complete base, because they all need to be perpendicular. But we call it the side vector. Say it can be calculated like this, using a cross product operation. So we could also define this instead and work out the up vector, but that is the convention. So this is just about the terminology and what we call stuff when we place a virtual camera. It's pretty intuitively easy to understand. The camera is just like an object in the world. Yep. The juicy bits of the viewing is, of course, how to do it in the transformation sense. How do we work out the matrix transformation, the transform matrix, based on this view? And we call that the view transform. Oh, actually, I wanted to put in most of the previous slide. Maybe a little smaller. So we've defined where we want to look. We want to work out the matrix. A bit of annotation. We define another matrix, which is not exactly what we want, but it's easier to define, so we start with that. A transform matrix that converts from world space into camera space. I'm going to put some colors in here to better be able to see that this is actually just the basis vectors, and also to relate it to this. A little confusing right now, but it should be clear. So this is actually the coordinates of the side vector. These are the coordinates of the up vector. And these are the coordinates of the view vector. And out here we have the coordinates of the translation. So as you see, this is a simple matrix to define. Of course, we need to put the fixed part as well. This is an affine transformation like everything else. There. This matrix is like the transformation from I'm sorry, this is actually a mistake. Let me just fix that. It's actually from the camera to the world. So if we had something, an object that was defined in camera space, we could use this matrix to transform it into the world space. and it is exactly the same like the model matrix we saw before, the object transformation. Now we want the inverse of that, because we want to transform everything that's in world space into camera space, so we know where it is in relation to the camera. So we simply invert this matrix, and then we have the proper view matrix that we want to use. There. I'm not gonna go into how to do this. It's matrix inversion is a basic operation, and actually it's a bit simpler to do in this case. You don't need to do a full inversion. You can, I think you can just transpose the linear part and negate the translation part, something like that. But it's not important. You don't need to do that operation. It's usually done by the hardware. You can use a command in a shader to invert a matrix. So we give this matrix to the system. We can perform the second step in the vertex transformation pipeline, view transformation. I think I want to do one more. Let me just check that. 13, yes. The final slide is about the third step in MVP projection. Or we're starting on that at least. So what is projection? Projection is how we convert 3D into 2D. How we put 3D geometry on a 2D screen.
Is this the second pipeline step?
Third pipeline step. And I think I have this one. Yeah, this is from the book. These two kinds of projection. We can do perspective projection or it's actually called orthographic parallel projection. No one says that in practice, just orthographic, which is hard enough. Perspective projection, where stuff gets smaller the further it gets. So it's basically mathematically it's just dividing by the z coordinate. It means that things will look as they do to us in real life. We of course see the world in perspective. Orthographic projection is more usually used for like 2D graphics. So you normally use 3D APIs for everything nowadays, and orthographic projection you use for 2D graphics, but you can also use it for stuff like what you call isometric 3D sometimes, of games that actually look at a 3D world from the side or from above and the side, but there's no perspective, so stuff doesn't get smaller when it's further away. This is also an orthographic projection. We are working here in what is called view space, the view coordinate system, which is the coordinate system of the camera that we saw before. And in order to achieve this, here it's quite a simple operation. It's dividing all the coordinates by, or the x and y coordinates by the z coordinate. And to do orthographic projection is even simpler. Discard the set coordinate. At this point we are in view space, so the set only tells us how far stuff is, and we just smash everything together on the screen. We just ignore the set coordinate. That will do that for us. Good. What time is it? It's almost